Okay, you guys. So in our last lecture, we started talking about the Heck reaction, one of the many cross-coupling reactions. And so I just want to remind you that the Heck reaction requires that you typically have an aryl, vinyl, or alkyl halide, or triflate. We've talked about triflate. I gave you the structure of triflate. You also need an alkene. And your alkene has to have at least one hydrogen on it. The reaction is palladium catalyzed. And you need a base. And we talked about the number of bases that you can use, the different bases that you can use to form your product, which is typically a trans product. But what's so significant about this reaction is, for the most part, you are forming carbon sp2 bonds bonded to other carbon sp2 bonds. Okay, so carbon sp2 bonds. And we went over the mechanism of this reaction. We talked about how the first step is an oxidative addition. The last step is a reductive elimination. We talked about how you have to rotate about a carbon-carbon bond to prepare the molecule to do a beta hydride elimination. I showed you arrows on the mechanism with respect to the beta hydride elimination and the migratory insertion. And so now what I'd like to do is jump into other cross-coupling reactions that are just as popular as the Heck reaction. Because again, Heck won the Nobel Prize in 2010 in chemistry, but he won it in partnership with two other great chemists. And so let me introduce their chemistry. And these are also cross-coupling reactions. And so the general reaction to these cross-coupling reactions requires that you also start with an aryl, vinyl, or alkyl halide, just like the Heck reaction. Or triflate. Now, in this case, you don't have to start with an alkene. What you can do is actually start with a different R group that's bonded to a metal that is not palladium. Okay. Just like in the Heck reaction, you need a palladium catalyst. Now, in some of these cross-coupling reactions, not all of them, you need an additive, also known as a base. And I'll tell you and show you when you do need this additive and when you don't need it. And so you can see some of the similarities between the Heck and the general cross-coupling reactions. They both need aryl vinyl alkyl halides. They both need a palladium catalyst. On occasion, they both need a base. And in this case, you typically form your bond between the two R groups, i.e., the R group that's bonded to a metal and the R group that holds the leaving group. Okay. Where, of course, the only difference is you're starting with an R group bonded to a metal as opposed to just an alkene with hydrogens and an alkyl group on it. Okay. And so, again, this is the general reaction of cross-coupling reactions. R2 can be an aryl, vinyl, or alkyl group. Our metal can be boron, And when it is a boron metal, it is known as the Suzuki cross-coupling reaction. When the metal is tin, oh, excuse me, it is known as the Stille cross-coupling reaction. I'm just going to say CC for cross-coupling. When the metal is copper, it is known as the Sonogashira Castro Stevens reaction. When the metal is magnesium, it is known as the Kumada reaction. When the metal is zinc, it is known as the Nagishi reaction. So these 5 reactions that I've just mentioned all follow the same general reaction scheme that I just showed you, where the only difference is, of course, the metal that's being employed for the reaction to occur. I'm not going to go over all of these 5 reactions because the mechanism is pretty general, but what I do want to go is I want to go over the first 3. And specifically, I want to go over the first 2 because Suzuki and Stille won the Nobel Prize with Heck in 2010. And so I definitely want to go get into their chemistry and the relevance behind it. But I also want to go over the Sonogashira and the Castro-Stevens because it is a huge part of our department. Dr. Spence does a lot of Sonogashira Castro-Steven coupling reactions, and I think it's really important to incorporate the research that we do into this specific lecture. Okay. So let me go ahead and remind you of a couple of the reactions that we talked about before in lecture 7 to help us out with these 3 reactions. So this is just a reminder from lecture 7. Now in lecture 7, we talked about transmetallation. And I showed you the mechanism, I showed you the reaction. I told you that it's typically a metal bonded to a ligand reacting with another metal bonded to a different ligand, and they sort of swap ligands. And so this reaction step is incredibly important for the 5 cross-coupling reactions that I'm going to show you. We talked about how the transmetallation step, the bonds being made, and the bonds being broken is all occurring at the same time. We talked about the 4-membered ring intermediate. And so it's really important that you remember that specific step. And if you need to go back, please feel free to do so. Okay. Okay, so let's first jump into the Suzuki reaction. And the Suzuki reaction is a really popular reaction in our research group too. We've used it to synthesize small organic bioactive molecules, and I'll give examples of that in a second as well. But let me first introduce the reaction. And if you remember, you use boron as your other metal. And so just like before, you need an aryl, vinyl, or alkyl halide or triflate. You need your R2 group bonded to boron. Boron can hold 3 substituents, and so I'll discuss the other 2 substituents that are bonded to boron. Just like the Heck reaction, you need a catalyst. It's typically palladium. And just like I mentioned in the previous lecture, triphenylphosphine isn't the only ligand that you can use, but for our purposes, we'll use the same catalyst that we use for the Heck reaction. You need an additive. That's typically a base. And you form your carbon sp2 bond typically. Okay. So before we go into the mechanism and before I show you examples, let's talk about a couple of things. Specifically, let's talk about the boron and the additive because we've seen these before in our Heck reaction, but I specifically want to talk about our boron and that Y group. Okay. So the boron is usually bonded to hydroxy groups or alkoxy groups. That's not to say that it can't be bonded to R groups as well, okay? i.e. alkyl groups. The difference between these is that the ones with hydroxy groups and alkoxy groups tend to be more stable and easier to use. The ones with alkyl groups are least stable. And so why is that? Boron is in our group 3. It has 3 valence electrons. It can only bond to 3 things. It has an empty orbital. And because it has an empty orbital and it's bonded to either hydroxy or alkoxy group that have lone pairs, you can donate electrons via resonance and satisfy that octet rule and stabilize your compound. R groups are also electron donating groups, but they're electron donating groups via hyperconjugation. And so you learned about hyperconjugation in Chem 24, 124, your sophomore organic chemistry. If you want to discuss hyperconjugation a little bit more, I'd be happy. Please feel free to come to office hours. But not surprisingly, the take-home message is that alkyl groups don't have lone pairs. And because they don't have lone pairs, they don't stabilize the boron as effectively as a substituent that does have lone pairs. And so it's not surprising these are the most commonly used boron substrates. Now let's move on to the additive that we use. And as I mentioned, the additive is a base. And just like in the Heck reaction, there are a number of bases that you can use. Sodium hydroxide, potassium hydroxide, alkoxide bases, cesium carbonates, potassium carbonate, if I'm not mistaken. In our research group, we tend to use potassium carbonate. And so what these additives do, and what I'll show you as we're talking about the mechanism, is it facilitates the transmetallation step. Ooh. Okay. So now let's jump into an example of this. And I'll provide more as I'm going along. So we've got our vinyl boron and our vinyl halide, palladium catalyst, in the presence of base and benzene. So for benzene, I'm just going to say phenyl with a hydrogen. Okay. And so let's jump into the mechanism of the reaction. Just like before, just like with the Heck reaction, you always start with your palladium catalyst. And if you remember from our previous lecture, we talked about how this has 14 electrons. And so this obviously catalyzes the reaction. Because it's a catalyst, we have to regenerate it. And so again, it is a cyclic catalytic cycle. We have to come back to it. And luckily for us, the first step is an oxidative addition. Oh, sorry, that looks a little messy. So let me draw that intermediate. Okay. Now, here's where things change and are different from the Heck reaction. In the Heck reaction, after we went through the oxidative addition step, the alkene came in, it complexed to the palladium, you do a migratory insertion, you rotate. In this case, that doesn't happen, right? There's no alkene. There's an alkene, but it's bonded to my boron, right? And so in this case, the next step is a transmetallation step, okay? But not just any transmetallation step. This isn't ready to go through transmetallation. So the first thing that you have to do for it to go through a transmetallation step is you have to prep it. So in your reaction round bottom, there's another step going on, and that's the prepping of this for it to undergo transmetallation. So what do I mean? So side reaction. The side reaction that's occurring is I take my vinyl boron. Okay. Let me actually move this a little bit over. I don't like that it's too crowded. Okay. This molecule won't transmetallate. And as I mentioned, the additive, i.e. the base, actually facilitates transmetallation. So what do I mean by that? If you add a base, like sodium hydroxide, or potassium carbonate, or cesium carbonate, it's a Lewis base. This is a Lewis acid. It attacks the boron. Lewis acids accept electrons. Lewis bases donate electrons, right? And so what you form is the complexation of the hydroxy group to the boron. And now I've got a negative charge on my boron. Now I've activated my boron. Well, Dr. Lucero, how have you activated this? The boron doesn't want to be negatively charged, right? If you guys remember from sodium borohydride, the boron doesn't want to be negative charged. And so because it doesn't want to be negatively charged, those electrons, that negative charge is given to the hydride source. That's why H minus is a great base and a great nucleophile. The same thing here. Boron doesn't want to be negatively charged. So those electrons go to your carbon. And now it's set up for transmetallation. And what I mean by that is this structure is added into the reaction and it swaps groups with the palladium. And the group that is swaps is the bromine. So the boron now has the bromine. And the palladium now has the two vinyl groups. So all they did was swap groups. The boron got the bromine and the palladium got the alkyl vinyl group. Okay. And now it does a reductive elimination step and it regenerates our catalyst. And not surprisingly, it couples the two carbons. And so if we draw that out, I'll draw it up here. If you need to number your carbons, number your carbons. I'll number it for you as well. Notice that carbon 2 has the methyl group, and carbon 2 is now bonded to carbon 3 because of that reductive elimination. That's where they're coupling. Carbon 3 is still bonded to carbon 4, and carbon 4 has two methyl groups. And so I'm done. That's it. That's all that happens. It's a much more concise, I think, mechanism than the Heck reaction. You don't have to rotate. You don't have to show any arrows of rotating or hydride eliminations. It's just a transmetallation step and the side reaction that's occurring to form your activated species that can go into the reaction. Okay. Okay. So let's talk about these vinyl boranes because these vinyl boranes are not commercially available. Okay. You actually have to make them. And so how do you make vinyl boranes? Okay, so in our research group, we typically form our vinyl boranes from an alkyne. And this is just the general reaction. And so this is exactly how a lot of groups do this. We start with an alkyne and we treat it with a borane. And the most popular borane out there is catechol borane. Okay. And so it proceeds via a hydroboration. And your sophomore organic chemistry, you learned that boranes can reduce alkynes and they can reduce alkenes, right? And so if you remember, it's really clever how it was developed. And luckily for us, it's a high-yielding reaction. This is a great review of sophomore organic chemistry. The first thing that you note is that the borane adds to the least substituted carbon. And not only does it add to the least substituted carbon, the borane and the hydrogen add in a syn fashion. And that's it. You form your vinyl borane. Excuse me. Let me move this over. Please notice that the substituents on the boron have lone pairs to stabilize that boron. And so once you make it, it's stable enough to go on and to use it where only one group is going to transfer over. This isn't a wedge. I'm just trying to make the point that this is the group that transfers over. Okay? Again, you typically need something with lone pairs. If you have something like BH3, then you're just going to keep reducing your alkyne. You're not forming a vinyl borane. You're just reducing it uh, all the way down, right? And you don't want that. You just want to reduce it once to form the vinyl borane and stop there. Once you form your vinyl borane, now you can go ahead and use it. So in our group, we form our vinyl borane, and then we treat it with our aryl halide. And we'll go through the mechanism. And I'll just write OR. We use our palladium catalyst. And our base. And so just like before, as always, our first step is oxidative addition. Our second step is transmetallation, but I can't do the transmetallation until I prep this vinyl borane. So my side reaction is the prepping. So I take my vinyl borane, I add my sodium hydroxide to activate my borane. Oh, sorry, that arrow wasn't heading towards the boron. Now it's negatively charged. Now it's ready to go into the reaction. And do a transmetallation. Just like before, once we do the transmetallation, they're exchanging substituents. And so my boron now has my bromine. And my palladium now has both vinyl groups. And now it can go ahead and do the reductive elimination. Again, notice how the reductive elimination occurs between the two carbons that are bonded to the palladium, right? That's where the bonding is going to occur. Once I do the reductive elimination, I regenerate my catalyst and I generate my product. And let me draw my product down here. And I have formed a new carbon sp2, carbon sp2 bond. Okay. And so in our research group, that's how we were able to introduce these long chains into the aromatic system. Okay. And so why did we choose the Suzuki reaction and not the Heck reaction? If clearly it's an alkene, and I can probably add an alkene to it and get the trans product. So it's an alkene and it's trans. What we were noticing for the Heck reaction is that once it did the beta hydride elimination, it added to the palladium again, and it was doing a migratory insertion, beta hydride elimination, all the way down the chain, just like I showed you before when I first started introducing organometallics. If you guys remember, I was showing you how a double bond migrates down a chain, and it was doing the exact same thing. The double bond in the Heck reaction was migrating all the way down, and it was migrating all the way down to form an alpha beta unsaturated system. Now, it wasn't the major product, it was a minor product, but it was enough that we didn't want to publish that work. And so, what we decided to do is instead of having it migrate and do beta hydride eliminations and all of that, let's just set the double bond immediately and let's just go through the Suzuki reaction. It won't migrate, it'll stay as is. It won't rotate, it won't do syn beta hydride eliminations. It'll just stay and not move. Okay, let me give you one last example before I move on to the next cross-coupling reaction. Okay. So not surprisingly, just like you can have intramolecular Heck reactions, you can have intramolecular Suzuki reactions. Okay. You can start off with your palladium catalyst. Oh, excuse me. And your first step is an oxidative addition. So if you notice, your vinyl halide is present and your vinyl borane is also present, all in the same molecule. Move this down just a little bit so I can give myself some space. I know it may be a little hard to draw seven-membered rings really quickly, so just take your time. So this is my oxidative addition step. I first have to activate my vinyl borane. So I've got my sodium hydroxide. Luckily for us, it's all happening in the same molecule. And now I've got my activated boron that can proceed to undergo transmetallation. Now, before I draw what the palladium system looks like, let me just first number my carbons and number my atoms so I know what's going on. So I've got 6 carbons plus the palladium, so I'm going to form what looks like a 7-membered ring. And there's my 7-membered ring, including my palladium, okay? Again, it's the carbon that's bonded to the boron that transmetallates and replaces that iodo group, right? And so that's the bond that you're forming between carbon-6 and palladium. So it's a 7-membered complex. And now I can do my reductive elimination step. Where I'm forming a 6-membered ring because it's the carbon-1 and carbon-6 that are forming a bond. So let me go ahead and draw that out. Oh, excuse me. I'll draw out my 7-membered ring first, and then I'll draw out my 6-membered ring. And so again, you see the new bond being formed, carbon-1 and carbon-6. Okay, so now let me go ahead and finish the Suzuki, the last couple of things regarding the Suzuki. We will come back to it. I just want to give you the general overview of the other reactions, but let me finish up the Suzuki reaction with a different example. Specifically, um, an alkyl example on the boron in the presence of my palladium catalyst and my base. To form my new bond, i.e. a carbon sp2, carbon sp3 bond. And so this is uh, pretty impressive because if you remember, um, in the Heck reaction, you really couldn't have carbon sp3s or beta hydrogens or anything like that. Um, but what Suzuki did was he figured that he could actually install the alkyl group on the boron system as opposed to the alkyl halide. And it really worked out pretty nicely. And so let me just talk about that. That wasn't a wedge, that was just a bond that I was trying to emphasize. And so why is it that he started introducing that and provided an alternative to the Heck reaction? And so if you look at the mechanism, you do your oxidative addition. Now, if you remember in the Heck reaction, we typically started with our alkyl halide as our oxidative addition step. And so we just, Astili, or Suzuki, excuse me, Suzuki said, nope, you're going to start with your aryl halide. You're not going to introduce the alkyl group until the very end. And so you still start with your aryl halide for the oxidative addition. Just like before, I've got my alkyl borane group that can't do transmetallation. I need to set it up and activate it. And so I have my side reaction going on. Treat it with sodium hydroxide. And now it's activated. Now it can go ahead and do a transmetallation. It's really clever how they figured this out. Excuse me. Just write phenyl group for my group. Now we're at the last step. Now you could either do beta hydride elimination or reductive elimination. Dry it out as well so I can prove my point. So that you can form your carbon sp2, carbon sp3 bond, right? They're the same thing. I just added phenyl instead. But the beauty of it is that Suzuki waited till the very last step to add his alkyl group in order to avoid the beta hydride elimination, and it can quickly go into the reductive elimination step and couple your two groups together. The other thing that's been done that's actually worked in our group as well, because we've used alkyl boranes, is we've changed the ligands. And we've changed the ligands so that they're bulkier ligands. And because they're bulky ligands, and I can, if you like to talk about that at office hours, that's perfectly fine. We've changed the ligands so that they're so bulky that they force the groups to bond. And so it avoids the formation of the beta hydride elimination, and it forces them to bond and form the reductive elimination step, or drives the reductive elimination step. Okay. And so we've added benzene rings to our ligand. We've added substituents, bulky substituents, so that we really have a huge angle and force the groups to bond, which is really clever. Okay, you guys, so that's the end of the Suzuki reaction. We will come back to variations of it, but let me finish up introducing the Stille and the Sanagashira Castro-Stevens reaction.